Sedimentation, rocks formed by surface processes. Sediments are produced on the Earth's surface as a result of weathering. We're going to see a couple different types of weathering and the results of those different types of weathering. Sediments are transported and become sedimentary rock after they come to rest and are lithified. That's the cementation of material into a rock. Sedimentary rocks record evidence of ancient sedimentary environments where they form. This is evidence such as climate, biology, chemistry. Lots of different evidence can be recorded by different components of ancient sedimentary rocks. In this lecture, we're going to cover surface processes of the rock cycle, sedimentary basins, which are sinks for sediment or repositories for sediment that's generated elsewhere, sedimentary environments, the kinds of environments that lead to the production of a sedimentary rock. Sedimentary structures, these are going to be evidence of how the sediment came together and how the rock formed. Burial and diagenesis. Burial is the compression and heating of sedimentary rock. Diagenesis is the chemical change. It essentially means born twice, born again. We'll cover classification of siliciclastic sediment and sedimentary rocks as one primary type of sedimentary rock, and then we'll get into classification of chemical and biological sediment and the sedimentary rocks that result from that. Starting off with surface processes in the rock cycle, we need to talk about weathering. This can be physical weathering, where rocks or precursor material is physically broken down. It's cracked, it's pulverized, it's beaten, it's grinded. Those kinds of things, those physical actions, are part of physical weathering. And we'll talk about chemical weathering. The simplest way to envision what's happening here is to put some rock salt in a bowl of water and watch it go away. That's really what's happening in chemical weathering with all kinds of sedimentary and precursor materials. When we discuss processes forming sedimentary rock, we need to consider weathering, where the material comes from. We need to consider erosion, how that material is initially transported. That plays a role in the appearance and the size of the material that's being weathered. Transportation, this further modifies material as it's moved over greater distances. And then deposition is going to impart certain characteristics on the sediment pile, which ultimately gets incorporated into the sedimentary rock. And we'll talk about burial and compaction. This is going to be important not only for the genesis of a sedimentary rock, but also the potential value of that sedimentary rock. The burial and compaction history may play a role in whether the rock contains valuable minerals or valuable fossil fuels. And then diagenesis. This is going to play a role in whether we can get those valuable materials back out of the rock in an economic way. So starting with the diagram here, weathering is going to break down rocks physically and chemically. Here in this diagram, we have a mountain range. It's been uplifted and it's going to be exposed to atmospheric activity such as wind, rain, snow, sleet, ice, hail, etc. That is going to physically degrade the rock. If the rain is acid rain, it's going to be more chemically reactive with that rock. So the rate of weathering is going to increase chemically if the amount of CO2 in the atmosphere increases, for example. Now, once this material is weathered, once it's broken up, erosion is going to carry the particles away down the slope. This material may end up in a glacier. It may end up blowing away. It may end up incorporated into debris flows, landslides, things of that nature that are going to move these particles downhill. Eventually, they may reach a point where they enter a river and they can be transported long distances. They could also be transported long distances by the wind. Much of the fertilization of the boreal forest here in Saskatchewan is derived from the deserts of Asia. So dust is blowing from the Tibetan Plateau in the Kagame Desert in China all the way across the Pacific to North America and even across North America. This transportation can be quite considerable. Deposition is when the sedimentation occurs after the flow of the water slows to the point that it can't carry the sediment or push the sediment along anymore, or if evaporation reduces the amount of water and eventually the dissolved materials become so concentrated that they precipitate. Ultimately, if the sediment survives all of that, it can be buried as layers of sediment. And it can be covered by other layers of sediment that press down upon it, compressing it, forcing those grains closer together, where cementation or lithification becomes easier. Diagenesis ultimately lithifies the sediment and or changes the cement that was existing previous. So it's a rebirth of the rock, essentially, the diagenesis. Now, when we talk about sediment, we need to classify it to better relay our information from one scientist to another. We need to put it into categories. Two primary categories: siliciclastic sediment, it is what it sounds like, particles of silicates. So silica particle sediment, bits and pieces of silicate rocks. Now, we know from the previous lecture that silicates make up about 95% of the rocks at the Earth's surface. And we have chemical sediment. This is what would be derived in an evaporating lake or an evaporating marine deposit. Lastly, we have biological sediment. This is composed of the bits and pieces of plants and animals, most readily seen in coal, made up of plants, or a coral reef made up of corals and algae. When we move material, we sort the material. In this case, the current strength and distance of transport are going to affect the size of the clastic particles, how big they are. The greater the distance, the smaller the particle at the other end of the process. These particles are going to be sorted based on size and density as they move, and they're going to be rounded based on their hardness as they move. Now, in a very simple diagram here, we can see that a short distance of transport, starting with an equant crystal, maybe a garnet, for instance, is going to result in a rounding, an increasing roundness of the grain. So we start out with a relatively equant grain with lots of points and other edges present. Those are going to wear off first. Ultimately, we're left with a nice spherical mineral grain. If the grains are large and more angular, they're going to become smaller and more rounded. So this doesn't mean spherical. It means that the edges have been worn away. Eventually, it's going to become more approximately a sphere, but in general, we're going to knock the edges off. To produce these chemical sediments, we need a chemical mixing vat. Our two primary chemical mixing vats are the oceans, evaporating ocean water, and evaporating lakes. We have a high altitude lake that is being fed ingredients from the weathering of the surrounding rocks. So all these rocks are going to break down physically and chemically. The chemical weathering of the particles is going to result in the chemistry of this lake. Therefore, the minerals that precipitate out of this lake are going to be related to the minerals that existed up here. They're not going to be the same minerals by any means, but they're going to have the same cations and the same anions as the precursor minerals here. Thought question for the chapter. A geologist is heard to say that a particular sandstone was derived from a granite. What information could she have gleaned from the sandstone to support this? What's she going to see in that sandstone that says, this was a granite? Well, think back to what makes up a granite. If the things that make up a granite are found in the sandstone, it's likely that that sandstone came from a granite. Just like if you find a big pile of car parts, it's likely those car parts came from a car. Describe the beach sands you would expect to be produced by the beating of waves on a coastal mountain range consisting largely of basalt. So just like the previous question, again, think about what's there in the first place. Describe the beach sands you would expect to be produced by the beating of waves, the physical weathering, on a coastal mountain range consisting largely of basalt. We're all sitting at home looking at our computers right now. Let's take a virtual cyber field trip to a weird place to answer this question. Other end of the Earth, traveling down to Antarctica. This was about 10 years ago. I was invited on the National Geographic Explorer to work on some of my penguin research down in the Antarctic islands. And this is the entrance to a small volcanic island. I'm going through Neptune's bellows here. It's about 90 mile an hour, 80, 90 mile an hour wind at this time, blowing hard enough that the wind blows in your nose and out your mouth while you're trying to talk, which makes it nearly impossible to talk. So it's a good breezy place just off the coast of Antarctica, so it's kind of wild weather. This is a view from the air. It's known as Deception Island because early explorers didn't know that you could sail inside the island right here. So that last picture I showed you was traveling through here, through Neptune's bellows, into this embayment, which is basically a caldera, a collapsed volcano. And for geographic fans out there, let's see. The island is going to be located right about here. So this is the southern tip of South America. Ushuaia is located around here. Cape Horn around here. This is the Antarctic Peninsula. So we're going to travel to this island here, which you can see a little better right here, shaped like a donut with a bite taken out of it. So this is a volcano. Therefore, it's going to be made up of volcanic rock. And this is what it looks like. See layers of basalt and volcanic ash. Now we're going to beat this coast with the Southern Ocean here. The Southern Ocean is almost always a wild place to be in terms of wind and waves. So it's a rough place to be a rock. As we get close to the beach here, we see an old whaling skiff here with some giant southern skua. These are the birds that eat penguins whenever they get the chance. So the enemy of the penguin is this giant bird. It also attacked my camera bag when I was trying to get some sleep on an island one day. Bad birds. Some Gentoo penguins doing a Gentoo penguin thing. And if you wondered how National Geographic photographers and videographers get their shots, this is Eduardo from Argentina and Jim, who's originally from Maine but now lives in Alberta. So get right down into the dirt with them. Now, what you can see here in this sand, and a little better here, is grains of volcanic material. These are physically weathered bits and pieces of basalt that have weathered from these cliffs, which are made of basalt. There was a weather station here until the 1990s when the volcano erupted and the station was destroyed by large volcanic bombs. It's active today, so when you see images like this is actually steam rising from the beach. We got the chance to go swimming out here, and the water's about -1.5 degrees. If you did that ice bucket challenge a couple years ago, that water is 0, and I will tell you, to save you the effort, that if you swim out here in this water, it's much, much worse than swimming in ice water. It's much colder than ice water. It's surprisingly uncomfortable. Back to something more comfortable. Sedimentary basins. Sediment tends to accumulate in depressions in the Earth's crust. Wherever there's a low point, material is going to accumulate. Dust bunnies accumulate in certain parts of your house or apartment. Sediment's going to accumulate in low points on the Earth's crust. Depressions are going to be formed by subsidence. That's one way. Sedimentary basins, then, are depressions that are filled with thick accumulations of sediment. They are sinks for sediment, or reservoirs for sediment. Well, there are lots of different types of sedimentary basins. We're going to consider 2 broad-scale types of sedimentary basins here. Rift basins and thermosubsidence basins, represented in this image by a photo from the East African Rift Valley, and flexural basins. Now, these sedimentary basins are going to form on rifted continental margins, the first category we're going to discuss. Starting here in East Africa, we have easternmost Africa rifting away from continental Africa here. Now, this rifting is going to result in these accommodation downdrop blocks that eventually are going to drop to the point that they're going to be below the surrounding ground level or ground elevation, and this is going to become a basin. When that happens, this basin, in the case of East Africa, is going to fill with water. In the case of Lake Malawi and Tanganyika, so on, these can be pretty deep lakes. So this rift is going to develop as hot mantle materials well up, going to rise, convect upward, here. The lithosphere is going to heat up, and it's going to stretch and thin out. As it stretches and thins out, the lithosphere above flexes downward. Transportation of particles via wind, water, and glaciers is going to bring material into this basin to accumulate as sediment. Also coming in and accumulating as sediment is going to be any biological material. Polar spreading, once this rift becomes exposed to marine water, is going to begin. And this subsidence is going to continue as the crust moves away from the spreading center, cools, and therefore becomes more dense. Ultimately, materials like evaporites and deltaic sediments and carbonates can be deposited along the margin here. If there's limited clastic sediment and the water is relatively warm, we'll often see development of a coral reef. If there's clastic sediment present, the water is usually too turbid. It's usually too cloudy, too many particles for the corals to withstand that. So corals usually don't survive in those types of environments. Some carbonates can, algal deposits can form, mixed with clastics. It's not quite as common. And the result is we can end up with a carbonate platform, in this case on both sides of the basin. These deposits ultimately could be buried by accumulation. So sediment piles on top forces the older sediment downward, where it can be compressed and heated, and ultimately it can even be metamorphosed. But on the way to metamorphism, it can be converted into a fairly dense carbonate rock or a siliciclastic rock. When we talk about sedimentary environments, we can break these environments into categories. We can subdivide the bulk of the types of sedimentary environments into components, categories. The first types of sedimentary environments we'll talk about are continental. These include lakes, like Premier Lake seen here, alluvial environments like Death Valley, desert environments like the Sahara, and glacial environments like that seen here in Antarctica. Shoreline sedimentary environments include delta environments like the Mississippi Delta, home for great sediment shrimp and music. Beach deposits like those seen here in Bora Bora. Tidal flats like those seen here in Belize. Marine deposits include deep sea deposits such as the Central Pacific, continental shelf deposits like that we'd see off the east coast of North America, organic reef deposits like we'd find off the southernmost coast of Florida in the Keys, continental margins like on the west coast of North America, and continental slope deposits. These would be off of the continental margin in deeper water.